Another trick I can use to simplify the analysis of my kinetics is to set up my reaction in such a way that I have a pseudo-order reaction. Let's see what we mean by a pseudo-order reaction. Let's take a look at our mechanism, which consists of consecutive reactions in which B is an intermediate. When the first equilibrium reaction was slow, we saw that we could apply the steady state approximation, and we came up with a rate law that was fairly complicated in terms of the concentration of C. However, when the first equilibrium was fast, we saw that we could apply the pre-equilibrium approximation, and we came up with a rate law that was second order overall. We can simplify both of these rate laws by judiciously picking the conditions under which we perform this reaction. If I use a large excess of the reactant C compared to the amount of A that I start with, then A will be the limiting reagent, and I will only make as much product as the amount of A that I have available. So if I start with A naught of A and C naught of C, and I make X amount of P at any given time, then I will have used up X amount of C and X amount of A. The maximum value of X is A naught. I can use up all the A naught. But if X is much, much less than C naught, A naught is much, much less than C naught, then the amount of C that I use up is small, and I can say that C remains at C naught during the entire reaction. So the concentration of C does not change during the reaction, whereas A does change. That simplifies each of these rate laws by keeping this concentration of C constant. In the pre-equilibrium equation, K2, KEQ, and C naught are all constants, and so I will lump those all together and call those my observed rate constant. And now I can see that the rate of this reaction is my observed rate constant times the concentration of A at any time, and I have reduced this second order rate law to a first order rate law. We say that this rate law is pseudo first order because I have forced it to be first order because of the conditions that I used in doing the reaction. In the case of the steady state reaction, we can see that K2, K1, K minus 1, and C naught are all constant, and so I will lump all of those together into an observed rate constant, and I can write that the rate is equal to the observed rate constant times the concentration of A, and so again I have reduced this complicated rate law into a first order rate law, so it is pseudo first order. The advantage of this is that first order reaction kinetics are fit by simple exponential functions, and those are easy to fit, and I can do a nonlinear fit which provides the observed rate constant for each reaction profile that I do. If I do this reaction under different concentrations of C naught, I will get different K observed because the K observed value depends on the amount of C that I begin with. In the case of the pre-equilibrium reaction, the observed rate constant is linear in the initial amount of C that I use. So if I graph the K observed values obtained by fitting these curves to the first order integrated rate law, I will get a straight line, and it should have a zero intercept because K observed is equal to K2 times KEQ, which is the slope of this line, times C naught, my X value, plus 0. In the case of a steady state mechanism, I would expect K observed to depend in a more complicated fashion on C naught. If I graph K observed as a function of C naught for this case, I will get a curve which levels off at higher values of the concentration of C naught. Thus, not only does making my reactions pseudo first order make the analysis of the reaction profiles easy because I have a simple equation that I can fit these curves to, it also allows me to distinguish between the pre-equilibrium case and the steady state case because I get a very different dependence of the observed rate constant on the amount of excess reagent that I use.